Welcome back to Nature and Code. We're in chapter 5, and in this video we will implement our offspring generation function. So in the previous video we just implemented this pick mating partner function where we pick a random mating partner given maximum mating distance. And now we need to create an offspring individual based on these two individuals, so the focal individual at grade III and the mating partner. And to do this, we will need to turn to an Austrian monk by the name of Gregor Mendel, who discovered the basic laws of genetics around 150 years ago. You may or may not have heard of him, but the important thing is that we will be implementing Mendelian inheritance, which is the basis for almost all biological inheritance. So the first law of Mendel states that alleles segregate during the formation of gametes and that each parent passes on one allele to the offspring individual. Now, this is not news to us. We have, this idea has formed the basis of our assumptions so far throughout, all the videos. Nevertheless, we're now implementing things on an individual level basis, so we just need to take a closer look at how we actually implement Mendelian inheritance given two genotypes who should produce one offspring individuals. Okay, so when we pick two parental individuals like we do here, the mating partner and the focal individuals, and each of them can have three possible genotypes, then there will be six possibilities of combination. We can combine A1A1 with A1A1, we can combine A1A1 with A1A2, and so on. And I prepared a slide here that shows these six combinations here. So you have parent 1 here, parent 2. In this case, parent 1 is A1A1. Here it's the heterozygote A1A2. And here it's A2A2 homozygote, and the same here on the left-hand side for the parent 1. And you could, of course, switch parent 1 and parent 2. Now, each of them produces gametes. In this case, the parent produces only A1 gametes. In this case, the parent produces both types of gametes with half-half. And in this case, again, the parent produces only one type of gamete, and the same logic applies here. And now you basically can combine the different gamete possibilities. Now here in the A1 case, you really only get one option. You only get the possibility of combining A1 alleles from the parent 1 with A1 alleles from the parent 2. And so you know that in 100% of the cases, you will get an A1 offspring. So there's little to think about in that case. Same is true in this possibility here. If both parents are A2A2 genotype, then in 100% of all cases, you will get an A2A2 individual as an offspring. Now, things get a little bit more interesting when the two genotypes are either not identical or if they're both heterozygous. So let's take a look at the heterozygous case. So let's assume that both individuals are A1, A2 heterozygote. That means they both produce equally many A1 alleles as they produce A2 alleles. That means the probability of them producing an A1 is 25%. Because you get 50% chance getting the A1 allele from parent 1 and 50% chance getting the A1 allele from parent 2. So that here's 25% probability. The same is true for A2A2. 50% chance getting the A2 from parent 1, 50% chance getting the A2 from parent 2. And then in all the other cases, you get one allele from one parent and the other allele from the other parent, and that makes up for the remaining 50%. All right, what about the other cases? We have a homozygote here mating with a heterozygote, and the same situation here, a homozygote mating with a heterozygote. The consequence of that is that in half of the cases, you get the homozygote. So that's 50% probability here, and the other 50% probability is that you get a heterozygote. And that is because one of the parents will only contribute one type of allele, and the other parent with 50% chance will contribute the same type of allele, which will give you the homozygote, and in 50% of the cases it will contribute the other allele, the other type, which will give you the heterozygote. And the same is true down here. So 50% the homozygote and 50% the heterozygote. And then there's the sixth case, in which case you have two homozygotes, but they're both different. So you have the A2A2 parent in one case and the A1A1 parent in the other case. This is actually quite simple because one parent will only produce one allele and the other parent will only produce one allele, which happens to be the other type. So in all cases, 100% of the cases, you get the heterozygote. All right, so this is Mendelian inheritance with 3 possible genotypes of diploid individuals, 2 alleles. So let's implement this in code. Let's switch to our code here. So here's our get offspring, where we call it. So let's implement it up here, function get offspring, and then we'll take 2 arguments, which are simply the individuals. So I'm going to call this, parent 1 and parent 2. And so in the book, I add these 2 extra lines here where I store parent 1 in a local variable called P1. And I do this simply to make sure that the code is a little shorter. Otherwise, in books you get ugly line breaks, and I wanted to avoid that wherever I could. But of course, you could just simply, in your code, you could just simply say, you're going to pass these, variables, and when you take them here in the function as arguments, you already name them P1 and P2. So then you can, avoid these 2 lines if you want to. All right, so just as long as you recognize that P1 and P2 stand for the 2 different parent individuals, everything, is working as it should. Good. So now we simply have to implement these 6 cases. So this is quite a bit of code, but it's actually very simple. You simply ask, what are the 2 individuals? In which of those 6 situations am I? And then, given a certain situation, knowing the probabilities of the offspring, you then basically, flip a coin and return the corresponding genotype. So let's go ahead and implement this. So our first, case that we'll be looking at is if both parents happen to be A1, A1. So P1 equals A1, A1, and this is the logical and that we encountered before, P2 equals A1, A1. In this case, it's quite simple. The function should just stop right there and return A1, A1. Yeah? Simple. So this is the first case. Let's perhaps take a look at the case where one of them is A1, A1, but the other happens to be A1, A2. So, else, if, let's say P1 is A1, A1, and P2 is A1, A2. Now, if that happens, then it's not a priori clear what's going to be returned, right? If you go back to the slide, you would see that in 50% of the cases we would return A1, A1, and in 50% of the cases we should return A1, A2. So let's implement exactly that. So let's just say if we draw a random number, and this number is smaller than 0.5. So this is like flipping a fair coin. Then we are going to return A1, A1. Otherwise, we are going to return A1, A2. So that's also fairly simple. Now, we have to be careful because we said, you know, the parents could be flipped. So this exact same situation would be true if P2 happened to be A1, A1, and P1 happened to be A1, A2, because you can flip these individuals, right? And it's still the same situation. So let's combine these two cases in here in one statement. So I'm just going to wrap this here in parentheses. And then I'm going to add a second case. So if that is the case here, if these two parents correspond to these genotypes, or if the same thing is true, so I'm just going to copy that. But now the P2 will be A1, A1, and the P1 will be A1, A2. So that's just the other case that we have to take care of. We didn't have to do this here necessarily. I mean, we could have, but it would have been unnecessary because this is a mirrored situation. You could write or if P2 equals A1, A1 and P1 equals A1, A1, but this is of course the exact same thing as this because it's the same genotype. All right, so we have taken care of combination number 2. Let's move on to the next combination. What is the next combination? Well, let's still assume that one of the individuals is A1, A1. Oops, double equals A1, A1. But that the other individual is not A1, A1 and not A1, A2, but rather A2, A2. Okay, A2, A2. What happens in this case? Well, as we've seen before, this case is actually quite easy again because this individual here will only contribute A1 alleles. This individual will only contribute A2 alleles. So we're guaranteed to get a A1, A2 genotype. So we can stop the function right there and return A1, A2. Now, once again, we have to be careful here. They're not the same genotypes here. So this could again be a situation where P2 happens to be A1, A1 and P1 happens to be A2, A2. So let me copy this as well. So let's add another condition here. Or the same condition, but now it's switched parents. Okay, moving on to the fourth case. Now, what if both of them are A1, A2? What about that? Okay, P1 equals A1, A2, and P2 equals A1, A2. Okay, both are heterozygotes. Now, this is the interesting case, right? The most interesting case, because we can get all the three outcomes here. It could be that both individuals provide the A1 allele, generating an A1, A1 homozygote. Both could be providing the A2 allele, generating an A2, A2 homozygote. And both could provide one allele, and one of them could provide one type of allele, and the other could provide the other type of the allele, generating a heterozygote. So we're going to use the same logic here as we have before when we initialized the Hardy-Weinberg frequencies. Remember, we used this idea of a line going from 0 to 1, and we have a pen sort of randomly falling anywhere on that line. This is what we did here. And we're going to do the exact same thing now down here. So we're going to draw a random number. And we're going to store this in this temporary variable random number. So this is our pen. Oops, sorry, semicolon. And now we can test for the 3 possible cases. So if this random number happens to be smaller than 0.25, then we will return an A1 individual. So that means in 25% of the cases, both parental individuals provided the A1 allele. If, on the other hand, so else if this random number happens to be, for example, larger than 0.75, which will happen in 25% of the cases, then we are going to return A2, A2. And in all the other cases, just in 50% of the cases, where the pen lands somewhere in the middle, we are going to return A1, A2. And that's the most complicated case, but we've just implemented it. And if you ask yourself, why do we need to store this in a random number? Well, because we will need this comparison, we make a comparison here twice, and this should of course be compared to the same number, to the same location where the pen landed on the line. Otherwise, if you would use math_random here and math_random here, you would essentially have 2 pens landing, and that wouldn't be accurate. All right, moving on. Oh, by the way, so again, we're talking about the exact same genotype here, so we don't have to, add another condition here, because swapping the parents here would be the exact same thing. All right, so now we have 4 cases. So what about the other 2 cases? So one of the cases is, one of the remaining cases is that P1 is an A1A2 individual, excuse me, and P2 is an A2A2. So this is in spirit the exact same thing as we have up here, right? One of them is a homozygote and the other is the heterozygote. So we can basically just copy this, or we can just implement it from scratch. So in this case, in half of the cases, so if math_random is smaller than 0.5, this will return the corresponding homozygote, so return A2, A2, and in the other 50% of the cases, we will generate the heterozygote. A1, A2. And once again, because these are not the exact same genotypes, we have to take care of the case where the parents could be switched. So I'm going to add this parenthesis here, or this condition, and now with the parents switched, the P2 could be the heterozygote and the P1 could be the A2A2 homozygote. Same outcome, of course. And the last case is very easy. We could just say else, but I'm just going to be here explicit. And I'm going to say, well, if P1 actually equals A2A2 and P2 is also equals A2A2, then of course we are going to we're going to return the A2A2 genotype. A2A2. And once again, because those 2 genotypes are identical, we don't need to have an extra statement here. Okay, so these are the 6 possible cases. And this, in fact, concludes not only this getOffspring function, but now our code is complete in terms of, running the generations. We are running the generations, we're picking random mating partners, and then we are generating an offspring individual. And then up here, or rather down here in the run generation, we're replacing the offspring, we're replacing the parental individuals with the offspring individuals, and we're done. So I guess what we need to do now is we need to print this to make sure that everything is working. So let's go ahead here in the run generation function. Before the generation counter increase here, we could just call a function print data. And again, this is a function we haven't implemented yet. So let's go ahead and define this function here, print data. And all this function should do is it should just go through the grid and basically, count how many of the different genotypes we have and then print that into the console. So let's go ahead and do that. We can, of course, use the variables that we already defined up here, right? We're using the A1 variables. So you could use, you could just say here A1 equals 0, just resetting these values. A1 equals 0, A2 equals 0. You could also put a var here so that you have local variables. It's fine too, because we're not going to use them anywhere else. And now let's implement a two-dimensional loop, and I'm just going to grab this one from up here because I'm a little tired of typing. And so this is the loop that iterates over the grid, and now we can say simply if grid I happens to be A1, then we're just going to increment that counter here by 1. And then the same for the A1, A2. So else if the element there is actually A1, A2, then we're going to increase the A1, A2 counter. And then if it's neither of those two, it must be A2, A2. So we're going to increase the A2 counter. And that's it. So all that's left for us to do down here after the loop has finished, and again, nice indentation will immediately tell you where that, which of the curly brackets here belongs to this opening curly bracket here. So I'm just going to say console log. And I first want to say which generation we're in so that we have some overview. So I'm just going to say generation, and then I'm going to use string concatenation here. And we have this generation counter, and maybe a semicolon, a colon to end this line. And then on the next line, I am going to print the 3 genotype counters, A1, 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 A2, and A2, A2. All right, and that's it. So let's save this, and let's go back to the browser, and let's reload this and see what happens here. So let's do this. Cannot read property undefined of undefined. So this is unfortunately a slightly vague error message. But Chrome is nice here and gives us an indication where exactly this happens. So we're returning grid JJJ here, and it seems to have an issue with that. So let's take a look. Let's take a look here. Where is this? This is up here. Return grid JJJ. So for some reason it seems to think J is undefined. So let's take a look where this happens. It could be because we're establishing J and JJ here. So one way to debug these things are just to print out things in the middle of your code to kind of see what's happening here. So maybe let's print out both J and the JJ here, and see if our code manages to do that. Okay, be sure to go back to the console and then reload. They're undefined up here already. Okay, so that's a problem. So there seems to be something wrong with this get random int. So let's see, maybe we somehow mistyped the max mating distance. Doesn't look like it. So maybe there's actually something wrong with the I and the II that we pass in here. So let's just remove this line and do a console log II. So again, this is sort of divide and conquer. We are now outputting here sort of as a sanity check to make sure that I and II are actually reasonable values. Let's go ahead and do that. All right, yes, in the first instance, of course, 0 and 0. This is the first index of the both of the indices in the beginning. So that seems to be fine. So there seems indeed to be a problem with our getRandomInt function. So let's go and take a look at it. So getRandomInt takes min and max, and then it floors mathrandom times max minus min plus 1. Oh, and then it actually doesn't return it. So it doesn't return anything. So there's a return missing here. Okay, so I apologize for this, but at the same time, I'm glad this happened because this is what will happen when you program. And it's really also important for you to learn how to basically find a problem in your code, because that will be, that will occupy almost 50% of your time, perhaps even more. Okay, so I think this was the error here. And let's see what we have here. We removed all the console logs, so this should work fine. So let's just save this and reload it, and indeed, everything now works fine. So we just had this one error. So we're starting here with these with the 25, 50%, 25, but then you can see very quickly things seem to be changing quite a bit. You seem to be losing quite a few heterozygotes. This number drops to 3,500 from 5,000 very quickly. So things seem to be working quite nicely. Now, as I promised in the beginning, this should be a really nice visualization. At the moment, we don't have any visualizations, so let's go ahead and implement that in the next video. See you in the next video.